So we're going to talk about acid-base behavior of amines today. So that's really, we don't really need to test on that on Friday. So we're going to do a lot of acid-base behavior, and then we're going to learn how to synthesize different amines. Okay, so there's a lot of synthesis in this chapter. So you know, I know you get really, after you've taken that test, you want to take about a week off. Don't recommend that because we got the final coming right around the corner. I also recommend that you, for practice, to get you ready for the synthesis after your test is over, then go back in chapter 18 and go to the end of the chapter in the synthesis section and just do some problems. Okay, so that will remind you of all the aromatic chemistry because there's a lot of aromatic chemistry here. Yeah? Will I have extra office hours this week? Yeah, how about 1 o'clock on Wednesday? Yeah? Okay, we'll add an extra office hour this week. All right. So we were talking about last time about beta-phenethylamines. And you'll notice there's two types. There's the beta-phenethylamine that has a no hydroxyl in the alpha position. That would be these guys all the way across. And then there's some that have the hydroxyl in the alpha position, right? These. Hydroxyl in the alpha position, no hydroxyl in the alpha position. We're going to learn how to synthesize both of those types. And some other types of amine also. All right. On the next page, we have some more amines that are not beta-phenethylamines, but are also so we have tricyclic antidepressants contain amines. Isocarboxazid, which is an MAO inhibitor, monoamine oxidase inhibitor. We have nicotine, we have Valium, we have Xanax. So you're seeing a lot of amines here, and so that's why we're going to learn how to synthesize. There's secobarbital, which is, we're going to actually do that this week in discussion. We're going to learn how to make those. So this is a barbiturate. And so barbiturates, if you look at this part of the molecule here, this is made from an active methylene compound. And then you just condense that with urea. So we're going to do that in discussion this week. That's old chemistry. Then we have cocaine, and what else do we have? Scroll down. Morphine and LSD. Okay, so a lot of drugs that affect the brain have nitrogens in them. So neuroleptic is what they call drugs that affect the brain. So important thing for you to be familiar with and a good target for us to learn how to synthesize some of these things. All right, so right now we're going to focus for the rest of today's lecture on acid-base behavior of amines. And we know that amine can act as a base, so we're starting off real simple here. Okay, so we mix an amine with the carboxylic acid. It makes sense that we're going to have a proton transfer. Methylammonium ion is what we get, plus our conjugate base. And so in order to see the direction of this equilibrium, we look for a conjugate acid-base pair. Here's our conjugate acid-base pair. The one with the extra proton is the acid. And then we do the same thing over here. We should have, if we do that, we should have one acid on each side of the equation. And this would be pKa about 5. And this is pKa about 10. So the reaction highly favored to the right. So we'll have just a little arrow going in the opposite direction here. So equilibrium favored to right. And at equilibrium, what do we have? And we saw in carbonyl chemistry, it's a good idea to figure out about how much we have at equilibrium of both species so we can make decisions about what's going to happen. So at equilibrium, we take a difference in the pKa, that's 5. So we would have 1 protonated carboxylic acid to every 10 to the 5th deprotonated. reactants to products. So the whole first part of this chapter is chapter 2 review. And then some of it is chapter 17 review, where we have aromatic amines and what kind of acid-base behavior do they exhibit. All right, so that's reaction of an amine as a base. We can also have reaction of amine as an acid. So mixing an ammonium ion with hydroxide ion, we're going to deprotonate. Could have that plus H2O. We can also, if we could take an amine that is not already protonated, okay, not an ammonium ion, but an amine that's not already protonated, if we treat it with a really strong base, then we can remove that proton also. So here's two examples of an amine acting as an acid. And remember, this is how we made LDA. All right, so what we're going to move on to talk about is substituent effects and how substituents affect acidity and basicity. We have the effect of alkyl substitution. We have inductive effects. We have resonance effects. There's also solvent effects, but in this textbook they're not talking about solvent effects, so we're going to leave that out also. All right, so test your knowledge. Question 1, which is the most acidic compound? What do you think? First one, second one, third one. All right, so this you're saying this one's, I heard first, most. And this would be least. Let's see why that is and see if that's right and see why that is. A good idea when we're trying to figure out acidity and basicity is to look at the conjugate base. And when we look at the conjugate base, we're looking for anything that might stabilize it, maybe destabilize it, and those are the factors that we're looking for. So conjugate base here would be ammonia. Conjugate base here. There's our conjugate base here, and then our conjugate base here has 2 alkyl groups bonded to nitrogen. All right, so are alkyl groups electron donating or electron withdrawing? They're electron donating. So what is that going to do to the stability here? This one has 1 ethyl group donating electrons to the nitrogen. This one has 2 electron donating groups. Which is the most electron-rich nitrogen? First one, second one, third one. Third one's most electron-rich. Okay, so this one has 2 electron donating ED ethyls. This one has 1 electron donating ethyl. So the 1 electron donating ethyl makes nitrogen more electron rich than ammonia. This one has 2 electron donating ethyls, so therefore it's going to be even more electron rich. So this one is less stable than ammonia. And the third one is even less stable. Remember, things that we do to stabilize the conjugate base make the acid more acidic. So in the second case and the third case, when it's less stable conjugate base, that means the acid's going to be less acidic. So here the conjugate acid is least acidic. And it's easy for students to get confused when we start going through this logic here. Just remember, the strongest acids have the weakest conjugate bases. So hydrochloric acid, pK -7, chloride ion is extremely weak base. So if we have, so that's how, you can always go back to that example if you get confused when we're talking about this. All right, how about this next one? Which amine is the most basic? First one or second one? First, I'm hearing more first one. Let's look and see what we have here. This methyl is electron donating group. EDG for electron donating group. That makes nitrogen more electron rich. This one over here, this aryl ring is electron withdrawing group in two ways. Or we should say aryl ring stabilizes the base in two ways. Number one is inductively. Okay, so that nitrogen here, this is an sp2 carbon. It's more electronegative than an sp3. So we're going to pull electron density towards that carbon. So sp2 carbon more electronegative. Than sp3. So we have a mild inductive effect from that adjacent phenyl ring. We also have it stabilized by resonance. So if we draw this ring here, that lone pair on nitrogen can be delocalized onto the ring. So this is also stabilized. So it's not only stabilized by inductive effects, it's also stabilized by resonance. Okay, and we can go here. So remember all those resonance structures we drew in chapter 18. That's why I want you to go back and review some of that. So you make sure that you're up to speed here, because it's been a while since we've had that. And it looks like we can draw one more. So let's draw one more resonance structure. We don't have any of this sort of delocalization in the first example for methylamine. So what we say here is that electrons are delocalized. And let's put brackets around that. So the electron pair is delocalized over entire ring. So therefore, it's a more stable, and therefore it's going to be less basic. Over here, we don't have any stabilization by resonance, and we have a destabilizing inductive effect. So this one's going to be more reactive. Or another way of saying that is less stable. And therefore, it's going to be more basic. So remember, when we're going in the same row of the periodic table, basicity parallels nucleophilicity. So we can make decisions based on basicity. So notice in this one, the first one we're asking about which one's more acidic. Here one we're asking which one's more basic. When we ask about acidity, we look at the conjugate base. When we ask about basicity, we just look at the base and see if there's anything stabilizing it. There's other ways to do this. You can look at the stability of the acid, but if for most compounds that we're dealing with, this is going to be a little bit easier to do. Questions so far? Anybody? All right. Now, this is the same question. Which amine is the most basic? And we're talking about the same exact ones, except now we're protonated and we're saying which one's more acidic. Okay, so I can ask you either kind of question, and I will on the final. Which amine is more acidic? So always look at the conjugate base. If the conjugate base is more stable, then the compound's more acidic. We just looked at the conjugate base on the previous page. So conjugate base, more stable. Therefore, this is more acidic. So I want you to feel comfortable going back and forth. I mean, and you're sophisticated enough here at the end of 51C that you should be able to do that. All right, how about this next one here, number 4. Which one's more basic? First one, second one, or third one? Third one most basic? Okay, let's write that. Happens to be the right answer, but you know, maybe I wouldn't write it if it wasn't the right answer. Most basic, which one's the least basic, would you say? Least basic? Okay. Somebody knows what they're doing here. Okay, so when we're talking about basicity, we don't draw the conjugate acid, we just look at the base strength and look for special stabilization. Now, all 3 of these can be stabilized by resonance, right? Boom, we move the electrons in, just like we did up here. All 3 can be stabilized by resonance. Okay, so I'm not going to draw resonance structures again. So what I'm going to look at is these ones that have these substituents here. And this nitro group, let's draw out the nitro group. I'm just going to draw right on top of it. And we know that that's an electron withdrawing group. We know that from chapter 18. So again, this is more indication that we really need to review chapter 18 to make sure that we're on top of things here. And so what you notice is we do have the resonance structures where we put the negative charge 3 places in the ring for all of these. But this one actually has another extra resonance structure here where we push electrons all the way onto the nitro group. So we get an extra resonance structure. Let me draw that extra resonance structure here. Again, I'm not going to draw all of them for each of these because they all have the same, but this one has an extra one. So what we have in this ring system is we have an electron, a very strong electron donating group and a very strong electron withdrawing group, ortho or para to each other. And if you have that situation where you have a really strong electron donating group, a really strong electron withdrawing group, ortho or para to each other, it makes for something that's very stable because one of the groups is pushing electrons and the other one is pulling them. So the electron rich is feeding right into the electron poor, and that makes for a especially stable resonance. So here we have extra, especially stable resonance structure. Therefore, this one is going to be the most stable. And by most stable, it means it's the least basic. The methoxy group, on the other hand, is an electron donating group. It's going to be putting electron density into the ring. Electron donating group makes the ring more electron rich. And it increases electron density near the amine group. Okay, so therefore this one is going to be the least stable or most basic. Questions on number 4? Question number 4, anybody? Here you look at the pKa's of the conjugate acids for these, and you can see it looks like it's not scrolling right, but we got the pKa's of the conjugate acids here. 4.6, pKa 1, and this one here is pKa 5.34. So exactly like we predicted. And that's always nice when we can use our predicting ability and we find out that we're actually right with what we think. So most acidic here. Therefore, the conjugate base is the most stable, just as we predicted. This one here is least acidic. Therefore, the conjugate base is least stable. All right, how about question 5? What are you thinking? First one, second one, third one, most basic. I heard second one very lightly. Anybody else want to second the secondary? Second the second one. Okay, which nitrogen is the most basic? Definitely this is correct. Most basic. This is due to hybridization effects. So may not remember hybridization effects. That again was back in chapter 2. So everything you learned all year is coming back here, right here in 51C. So let's remind ourselves what hybridization effect is. If we look at each of these compounds here, the lone pair is in an sp2 orbital. This lone pair right here is in an sp3. And this lone pair is in an sp. And so that nitrogen there is sp hybridized, and we know that a nitrogen that's sp hybridized is more electronegative than a nitrogen that's sp3 hybridized. So that lone pair is going to be more stable on the sp nitrogen. Okay, and so that's because when you hybridize, when you make sp3, you combine one s and 3 p's. So the sp3 orbital is going to look more like a p orbital than an s orbital. When you combine one s and one p, and this example here of the sp, it looks a lot more like an s than a p. And we know what an s orbital looks like. S orbital looks like this, a high electron density around the nucleus. So this is an s orbital. And that we know when we have a p orbital, electron density is on average further from the nucleus. So if we have half s and half p, those electrons are closer to the nucleus, as we show here in this third picture here. All right, so for this one here, electrons closer to the nucleus. That means they're held more tightly. We can approximate this. If you didn't have, I talked about this in 51A. If you didn't have me for 51A, how we can approximate this is we know that there's the positively charged nucleus and we know there's electrons. And we can approximate that by thinking about really strong magnets. If you have a really strong magnet and you line them up so they're attracted, when you hold them really far apart, you can't feel any force pulling them close together. As you get closer and closer and closer, you feel them wanting to pull together. And if it's a really strong magnet, you probably are going to have a hard time keeping them from coming in contact with each other. So as these get closer to the nucleus, they're held more tightly, and that's going to make it more stable. Less available for reaction. A couple ways of saying this. Less available for reaction, more stable. Over here, electrons farther from the nucleus. Therefore, more available for reaction, less tightly held. And therefore, it's just going to be less stable. All right, so that's why this is the most basic, is because there is less S character. Electrons less tightly held because they're further away. So this is going to be less stable, therefore more basic. All right, and this is actually a very large effect, especially when you get to sp hybridized atoms. Compare the pKa's of the conjugate acids. You do not need to memorize these numbers, but this one here is pKa minus 10. Here's pKa about 10. And this is pKa about 5. So a really pronounced effect, especially when you get to sp hybridized atoms. Questions on number 5, anybody? So I may have you on the test, I might ask you which is the most basic, which is the least basic. I may have you rank, okay? So you want to be prepared for both types of questions. What about number 6? Which one's the most basic? First one or second one? What do you think? I'm hearing a lot of first, and that's correct. All right, so this one here, more stable due to inductive and resonance effects. Let's look at inductive effect first. So what do we know about a carbonyl? Is that an electron withdrawing group or electron donating group? From chapter 18, we know that that's an electron withdrawing group. So inductively is pulling electron density away, making nitrogen less electron rich, right? The carbonyl is powerfully electron withdrawing. This makes nitrogen less electron rich. And therefore, more stable. And more stable equals less basic. So may not have even thought about the inductive effect of the carbonyl group, but it's certainly there. We also have a really powerful resonance effect. Okay, and we know that amides are stabilized by resonance. And that's really important for an amide because the nitrogen's pretty basic. So because it's pretty basic, it likes to donate its electron density. And so here we have here the amide. It's going to want to donate electron density to the, and remember this had a really high boiling point because of the fact that it has a very, very large dipole moment due to this second resonance structure that I've drawn. We, of course, can also have the one where we just push electrons onto oxygen and leave the nitrogen there. So we drew 3 resonance structures for this. This is a very minor resonance structure. But we do have resonance stabilization. And so because that lone pair on nitrogen is delocalized, it's going to be less available for reaction. So therefore, it's going to be more stable, and that equals less basic. Questions on number 6? Anybody? All right, so now we're going to jump ahead to chapter 17 and talk about aromatic heterocycles and acidity and basicity. I'm not a favorite of you guys, but let's talk about that. That may be something that you might need to review because, you know, the things that we learn at the end of the quarter aren't learned as well. And that was at the very end of 51B. Everyone was ready to go home for the holidays, and so it's, you know, you may need to review it. Okay. So when considering acidity and basicity of aromatic heterocycles, keep in mind, if nitrogen is part of a double bond, then the lone pair is not part of the aromatic pi system, and the nitrogen, the lone pair, is free to act as a base. If instead the lone pair is actually, remember we rehybridized, we put the lone pair into a p orbital and made that ring aromatic. If that lone pair is making that ring aromatic, it's not going to act as a base. It would much rather stay aromatic than act as a base. Okay, so again, a lot of you will need to review that. So, so what we're saying here is this nitrogen is part of a double bond. Therefore, this lone pair is not part of the aromatic pi system. And so this is what the structure looks like. So this nitrogen here is part of a double bond. It is sp2 hybridized. And so here this lone pair is actually in an is actually perpendicular to the p orbitals in the ring. It is that lone pair is in an sp2 orbital. And because that lone pair is not involved in aromaticity at all, it has nothing to do with that ring being aromatic, we can use that nitrogen as a base, and we're used to that. We used nitrogen as a base a lot, right? We did that in chapter 9. Maybe some other chapters sprinkled here and there. So we know that the nitrogen is going to be basic. So let's label that. Let's do one more label. So therefore, the nitrogen is free to act as a base. All right, in the second situation, this was one of those ones where we had to take that lone pair on nitrogen, and we had to put it in a p orbital in order to make this ring aromatic. Remember, we needed 6 pi electrons, 4n plus 2 pi. So nitrogen is not part of a double bond. Or certainly before we rehybridize it, it's not part of a double bond. And so therefore the lone pair is part of the aromatic pi system. So you know, this is really not like chapter 17. Chapter 17, you were deciding whether that was aromatic or not. Now we're telling you it's aromatic and saying, okay, the fact that it's aromatic, what does that mean about that lone pair? That lone pair is tied up making this ring aromatic. So that lone pair is part of the pi system. Part of the aromatic pi system. And what that means is that if we protonate nitrogen, that ring's no longer going to be aromatic. That's not going to happen, right? We're not going to protonate nitrogen and make that ring not aromatic. And in fact, you actually can protonate this ring. It does not protonate on nitrogen. It actually protonates on carbon. We're not going to talk about that. But you are not ever going to protonate on nitrogen here. Okay, so therefore, nitrogen is not free to act as a base. All right, and so this is going to help us make decisions about these guys as acids and bases. When we have oxygen, and again, might need to go back and review in chapter 17. If oxygen is part of an aromatic ring, only one lone pair is part of the aromatic pi system. Okay, so one lone pair is part of the aromatic pi system. And the other lone pair is not. Is not part of the aromatic pi system. So that's what it would look like here. So this lone pair is part of the aromatic pi system. This lone pair, you can protonate that lone pair. This lone pair is perpendicular to the aromatic pi system. And so that means that you can protonate that oxygen. So you can protonate here. All right, so let's see how we're going to use this to make decisions about acidity and basicity. So if we look at Perol, for example, do you expect Perol to be very basic? What do you think? No. Lone pair is part of the aromatic pi system. It's part of the aromatic pi system, therefore if you protonate you lose aromaticity. Not going to happen. So that means we have no protonated pyrrole. You will not find this. Let's put a big X through that. What about deprotonation of pyrrole? Can we deprotonate pyrrole? Well, if we deprotonate pyrrole, it's going to look like this. Is that okay? That's isoelectronic with furan, right? So if we take base, and we deprotonate, that's going to look like furan. And in fact, we can remove that base. This is pKa approximately 15. We can remove that base. This is still aromatic. Looks like this. Okay, so this is p orbital here. This is an sp2. And looks like furan. All right, so let's compare the pKa of pyrrole with that of ammonia. All right, so we do the same thing with ammonia. And let's compare that with deprotonating pyrrole. This one actually has a pKa of 36. And it turns out that pyrrole is in here. The lone pairs are in an sp2 orbital. Here, lone pairs are in sp2 orbital. Here, the lone pairs are, I'm sorry, sp3 orbital. What am I saying? Here, the lone pairs are in sp3. Let me fix that. Lone pairs are in sp3 orbital. And above the lone pairs, we're in an sp2. What's more stable? It's more stable to have lone pairs in an sp2 orbital, right? Okay, so it's less stable conjugate base than above. Less stable conjugate base than above, therefore the amine is going to be less acidic. So it makes sense that pyrrole is more acidic than ammonia because of the stability of the conjugate base. All right, so let's write the answer to that down. Why is pyrrole more acidic than ammonia? It has a more stable conjugate base. And that's because the lone pair is in an sp2 orbital. Which means we have more S character. Therefore, electrons are closer to the nucleus. And therefore held more tightly. Therefore, it's a more stable conjugate base. So all of these things are true. So gotta bet that if I'm spending a whole lecture talking about acidity and basicity, that you're going to have questions on the final on acidity and basicity guaranteed. Where's my scroll bar? Why are you? There we go. Questions? What about pyridine? Do you expect pyridine to be very basic? Well, gosh, we used it as a base all throughout chapter 9 at least. right? So yes, we do. I would. Lone pair is not part of the aromatic pi system. Therefore, protonation does not disrupt aromaticity. All right, so when we protonate, when you protonate pyrrole, which we've done a number of times, this acid has a pKa of 5.2. Compare this with the sp3 counterpart, which would be just ammonium ion. And this one has a pKa of pKa of about 10. And so we have a more acidic conjugate acid. Because the conjugate base is more stable. Why? Lone pairs are in an sp2 orbital rather than an sp3. For ammonium ion, the lone pairs are in an sp3 orbital. For protonated pyridinium ion, the lone pair, for the conjugate base, the lone pairs are in an sp2 orbital. It's going to be more stable to have those lone pairs in an sp2 orbital. All right, so this helps us when we have some of these heterocycles that you see in bio. You'll see these appearing. Things like histidine, things like that. And we want to be able to predict acidity and basicity of these compounds. So let's look at imidazole. Reactions of imidazole as an acid or base are important in many biological systems. And now, hopefully, you're going to be able to look at that and tell me what happens if we add acid to this. Where are we going to protonate? Top or bottom nitrogen? Top. Isn't that cool? Now you can do that. That's awesome, really. This lone pair is not part of the pi system. Therefore, you will protonate here. The other lone pair is not available for reaction because this is part of the aromatic pi system. Therefore, will not protonate here. So pretty easy job right now to draw the conjugate base. May ask you, conjugate acid may ask you to do that on a test. Who knows? This is what you'll get. When you add acid, you'll protonate on that nitrogen. Yes?
Do you mean to write that the lone pair is not part of the pi system, so it will be protonate?
Lone pair is, yes, lone pair not. Let's fix that. Thank you so much for catching that, because I would have had lone pair not part of the, oh, I put the not in the wrong spot. Lone pair, Lone pair. Not. How about that? Is that good? Lone pair not part of aromatic pi system. We'll continue this next time.